Technical rescue systems need to be strong, of course, but how strong do they need to be? There are a few methods that rescuers use to ensure that their systems are strong enough to operate safely. All of those systems start with an understanding of forces. We can assume that a single rescuer hanging from the end of a rope in vertical terrain puts approximately 1 kilonewton of force on the system. If that rescuer has a patient in a litter, then we assume about 2 kilonewtons of force on the system. Of course, these are theoretical numbers, and in reality, the forces will vary depending on patient weight, rescuer weight, equipment, friction, terrain, and so on. For many years, rescue teams have relied on static safety factors to build strong, safe systems. Static safety factors simply mean you take your anticipated static force and multiply it by the factor to arrive at a desired system strength. A common static safety factor you'll see in the mountain rescue world is 10 to 1. So with a 2 kilonewton load consisting of a rescuer, a patient, and a litter, we'd multiply by 10 and arrive at a 20 kilonewton minimum braking strength for all system components. Pretty straightforward, right? That 20 kN number has become pretty common in technical rescue as a baseline for system strength based on the math that we just did. You can also work backwards from your static safety factor by looking at the weakest link in the system versus your expected forces. So for example, if your weakest link is a 36 kilonewton rigging plate, you can divide 36 by your static safety factor to arrive at your maximum allowable system force. So with a 10 to 1 factor, that example would be a 3.6 kN maximum force. So a single rescuer is 1 kilonewton and a 2-person load is 2 kilonewtons. What if we need to put a second litter attendant on the system due to the complexities of terrain or the demands of patient care and packaging? That 3-person load in the vertical puts about 3 kN of static force on the anchors. So with a 10 to 1 static safety factor, we would need to build our systems to a 30 kilonewton minimum braking strength. Now, is 10 to 1 the right static safety factor? Over the years, some teams have interpreted NFPA standards to require a 15 to 1 static safety factor. I've even heard of teams trying to be extra safe and claiming to adhere to a 20 to 1 static safety factor. Now, let's think critically about that. What if we want to use the same materials to build a high line so we can tram a patient across a shallow canyon with a river at the bottom? On a long high line, it is very possible to see static forces of 4 to 5 kilonewtons on the track lines when the load is at mid-span. That means with a static safety factor of 10 to 1, we need to build our systems with a minimum braking strength of 40 to 50 kilonewtons. At 15 to 1, we need to build to 75 kilonewtons, and at 20 to 1, 100 kN. To put that into perspective, the Petzl paw rigging plate has a 50 kilonewton rating, so we need to double those on each line. So we end up with massive anchors, multiple rigging plates, prussic bypasses, tensionless anchors, doubled steel carabiners, 13mm ropes, and so on. Mountain rescue teams recognized years ago that this is totally unrealistic, also unnecessary, and often unachievable. And they were accomplishing missions safely with significantly less overall system strength, often around 20 kN. So some teams started using static safety factors as low as 4 to 1, recognizing that the real-life forces in rope rescue systems very rarely require 40 or 50 or 100 kilonewtons of strength. So static safety factors have built a huge margin of strength into our rescue systems over the years, but often result in dramatically overbuilt systems with heavy equipment. This may be fine in structure fire, but in mountain rescue, weight can be a huge factor. So, is there a better way to look at rescue forces and safety margins? Another approach is to consider instead a dynamic safety factor, in which systems are built to handle a multiple of the largest dynamic event expected. For example, consider a 2-line system with a rescuer and a patient in the vertical. We know that's a static force of around 2 kilonewtons, but if there were a single line failure, the jolt or oscillation load may be 2.5 times that static load. So with our 2-person load, that 2 kN on the system might turn into 5 kilonewtons in a dynamic event. So if you're using a 2 to 1 dynamic safety factor, you'd need to build your systems to a minimum braking strength of 10 kilonewtons in that event. If you're using a 4 to 1 dynamic safety factor, then you'd be shooting for 20 kilonewtons. The problem is it's really difficult to anticipate the maximum dynamic event in every circumstance. So properly deciding on a dynamic safety factor is difficult, especially in mountain environments where the terrain and equipment available may dictate your tactics. So let's look at another option. In 2014, Kirk Mauthner wrote an article entitled "Moving Beyond the 10-to-1 Static System Safety Factor, Introducing Force-Limiting Systems and Managing the Right Risk at the Right Time." In that article, he described the pros and cons to static safety factors and introduced a likely more realistic concept to determine overall system strength, which is called the force limitation model. Force limitation starts with the rescuer. That's a whole nother rabbit hole, but for our purposes, let's accept that it's generally agreed upon that we don't want to cause forces of more than 6 kilonewtons on the human body. I talk more about that in my video on rescue forces, but the bottom line is that we don't want to hurt people, and more than 6 kilonewtons probably will. So if we have a 2-person rescue package, that is a rescuer plus a patient, the force limitation model suggests building systems that will limit the overall forces to no more than 12 kilonewtons for those people, as the forces will be shared more or less equally between them both. We could see forces that exceed 12 kilonewtons in an edge transition gone horribly wrong with a small length of rope in service, or maybe on a high line where the tensioning haul team gets a little carried away. The force limitation idea has us building systems that will absorb and dissipate those high forces, though, so that our rescuers and anchors and equipment never see more than that 12 kilonewton max. Now, this idea is nothing new for rock climbers. In recreational climbing, we use stretchy ropes to limit forces. But in rope rescue, we also need to minimize stopping distance. Dropping 15 or 20 feet due to dynamic elongation with a loaded litter in your lap is simply not a safe option in complex cliffside environment. So if we can't use rope stretch to absorb force, what can we use? Have you heard of screamers? So this is basically a doubled over piece of webbing with some sewing that, in the event of a fall, will rip and absorb force. They're common for difficult aid climbing and in ice climbing as well, and they've been popping up more and more in fall protection systems for rope rescue and for rope access work. However, they have some drawbacks. There's been a ton of debate about whether they actually limit forces, and while the consensus is that yes, they do seem to work, they have limits. Namely, they can only absorb so much force before being spent. When this thing elongates the whole way, it no longer acts as a force absorber, it just is a sling at that point. Perhaps more importantly, though, is that after deployed, a system relying on screamers has no further means of force limitation. That means that from the moment a significant force happens, rescuers may be exposed to life-threatening peak forces in a situation that's already led to one incident. That doesn't make me feel particularly comfortable with using screamers as a force limitation tool in a rescue system. We want it to remain fully functional after a worst-case incident. So a better idea is to create a system that will slip to absorb force on the anchor side, but then re-grip quickly to prevent the load from dropping a long distance. Mauthner identified 6 to 12 kilonewtons as the range within which the system should slip and re-grip to limit force. So why 6 kilonewtons is a lower limit? As I said earlier, we could see jolt forces of 5 or 6 kilonewtons from the rescuers bouncing around, or the litter getting hung up and released, or a failure of one line. If the system slips at less than 6 kN, the result would be what we call inertial runaway. That is, the load would fall to the ground with nothing grabbing it in the course of those routine forces that we might see in rescue systems. We talked about why 12 kN is the upper limit already. All of the system components share forces equally. So if we have a rescuer and a patient at the end of a system that experiences 12 kN, then each is going to feel approximately 6 kN, which is that agreed upon safe limit for the human body. So if we adopt a force limitation model with 6 to 12 kN as the maximum possible peak force, does that mean you need to build systems to a 12 kilonewton minimum braking strength? Of course not. We still want a margin of safety, and we need the system to remain fully functional after a worst-case load. So a rule of thumb that we can follow that comes from civil engineering for live, fluctuating loads is a margin of between 1.5 and 2 times the largest anticipated load. So if we're creating a system that limits peak forces to between 6 and 12 kilonewtons, multiplying that by 1.5 to 2 times, we arrive at a minimum braking strength for that system of between 18 and 24 kilonewtons. Now, that is very similar to the 20 kilonewton rule of thumb that we often arrived at via a 10-to-1 static safety factor, but the way we arrive at that number is very different, and this becomes super obvious when we're evaluating different systems. Let's look again at that high line. We said earlier that we might see forces of 4 to 5 kilonewtons on the tracks at midspan, which means 50 kilonewton anchors in a 10-to-1 static safety factor system. But if we design the system to safely limit forces to between 6 and 12 kilonewtons and build in a 1.5 to 2 times safety buffer, then we need anchors that will support between 18 and 24 kilonewtons. Same thing for guiding lines, for steep angle lowers, and so on and so forth. Another convenient side benefit to force limiting systems is that on a raising operation, we don't have to worry as much about haul factors either. In the past, we have multiplied the number of haulers times the mechanical advantage present in a system to arrive at a haul factor. For example, 3 haulers pulling on a 5-to-1 gives us a haul factor of 15. Rescuers typically limit their haul factor to between 12 and 25, depending on the system design. However, with a force limiting system, we can push those limits knowing that the system will slip and re-grip and limit force if we exceed the design parameters. This isn't a license to go crazy, but more like an emergency release valve on a pressure cooker. It's still prudent to use load cells and keep an eye on max forces when performing large deflection operations. So how do you build force-limiting systems? Well, aside from dropping a screamer into the system, which we've already discussed, there are 2 better approaches. The first is to use purpose-built devices like the MPD or clutch, both for descent control on lowering and as a progress capture on the raise. These devices are engineered and machined to slip and re-grip at precise tolerances, creating safe force limitation in systems. They facilitate very rapid, easy changeovers from lower to raise and vice versa. For many rescue teams, this is the answer to modern rope rescue system design. However, they're also heavy, expensive, and they only work with 11 mil or 13 millimeter ropes. So instead, many mountain rescue teams are using what we call component-based systems, pairing a descent control device like the Conterra Scarab or a Black Diamond ATC with a nylon 3-wrapped prussik on a redirected brake strand, or a Technora Blue Water VT prussik on the load strand in a max over 1 configuration to provide auto stop should the operators lose control or become injured. I talk more about friction hitches and where to put them when building component-based systems in my other videos. The major drawback to component-based systems is that they need to be tested. Just like John Dill recognized back in 1991, slapping any combination of rope, descent control device, and friction hitch together does not necessarily translate to a safe rescue belay. The forces we can create in rescue are different from recreational climbing, so when we start to repurpose climbing devices like the Black Diamond ATC for rescue, it's important that we test the systems together to make sure they will function in a worst-case scenario. New materials combinations, like nylon prussiks on Technora sheathed ropes or vice versa, may also behave in unexpected ways. Only with drop testing can we actually know how a given system will perform. So to summarize, static safety factors have served well enough for a very long time, but often result in overbuilt systems. Dynamic safety factors are difficult to estimate and implement. A modern force-limiting approach allows flexibility and realism without resorting to guesswork about potential dynamic loads. Purpose-built devices like the MPD and clutch provide both reliable force limitation and ease of use with some materials restrictions, while component-based systems are lightweight and flexible with respect to materials combinations, but demand more technical skill and understanding from the rope rescue technicians operating them. I hope this video helps put rescue system design into perspective for you. I'll drop some additional reading in the description. As always, please leave any comments or questions that you have in the comment section below. I'm eager to hear your thoughts. Thanks for watching.